Hello, my name is Tony Lentz with FCT Assembly, and I'm going to talk to you about Fill the Void 3. It's a third part of a series of papers we're presenting on methods of mitigating voids in solder joints. First, we'll go over a brief introduction on voids and the types of voids that we're talking about. We will review the factors that influence voiding, the experimental methodology that we use to set up our testing, including the circuit boards and the components and the equipment that we're using. Then we have lots of voiding results to discuss of all the tests that we ran. From the voiding results we can draw some conclusions, and we have plans for future work and other tests we would like to run in order to optimize ways of reducing voiding. I've got some acknowledgements to thank people that helped me work on this data, and then we would have time for questions and answers in a normal presentation, but if you have questions, please email or contact me with the contact information that's at the end of this presentation. Here's the types of voids that we're talking about. These are voids in QFN thermal pads. And you can see here the void area probably between 15 and 25% roughly, which is a fairly high void area in a QFN thermal pad. So the problem with these types of voids is that they can limit heat transfer out of this component, which can lead to premature overheating failure. These voids can also lower mechanical strength in this type of solder joint and other types of solder joints, where the solder joint can actually fracture at some point during its life. And then long-term reliability issues can occur based on high levels of voiding. So voids can create trouble in your circuit board, maybe not today, but later on in the life of that electronic device, problems can occur due to voids. Here are some of the factors that influence voiding. The print dispense process obviously plays a role. Temperature and humidity, the printed volume of the solder paste, how complete is the brick, how much air is trapped in the solder paste when you print it. Air by itself in the solder paste can lead to a void in that solder joint. The storage conditions or environmental conditions around the solder paste while you're using it can play a big role, especially with water-soluble solder pastes. They tend to absorb moisture out of the air over time, and the longer they're sitting open on the printer, the more moisture they will absorb. Moisture directly turns into water vapor during reflow, creating voiding. The reflow conditions play a big role. The reflow profile that you set up, the different temperatures for soaks and peaks and time above liquidus, ramp rates, all those things play a role. The atmosphere that you use in your reflow oven can also play a role. Nitrogen in the oven can actually reduce voiding for certain solder pastes, and certainly reflow with vacuum can have a big effect on voiding. The substrates or components play a big role in voiding. Substrates meaning the circuit board and the surface finish, and the component and its surface finish and the conditions of those. The oxide level on the components and the oxide level on the circuit board finish can interfere with wetting, and if solder paste wetting is incomplete, that creates voids. And then the solder paste plays a big role in voiding. Usually people blame the solder paste for creating voids, and if you didn't have solder paste there and you were soldering with something else, voiding would probably be reduced dramatically. Because the flux contributes to voiding and the lack of wetting contributes to voiding. But solder paste isn't the only factor. These other factors have to interact with the solder paste in order to optimize or minimize voiding. Here are factors that we studied previously in our first two papers about voiding. Solder pastes, we studied a wide array of solder pastes. Solder powder types, we were looking at different particle sizes, type 3 versus type 4 and type 5, to see what effect that had on voids. We did some different stencil design considerations on these thermal pads. You can see here we studied a regular window pane. We studied a 5-dot pattern. We took a look at a rotated window pane and then just a diagonal stripe pattern, and that's published in our previous papers. We also studied two different surface finishes and their effects on voiding, ENIG and OSP surface finish. And then we optimized the reflow profile and did some different things with the reflow profile to see what effect it would have on different solder pastes in terms of voiding. We also used nitrogen in reflow for a test. Like I said earlier, nitrogen definitely reduced voiding for one type of solder paste, but had very little effect on other solder pastes. And then vapor phase with vacuum was also tested in order to determine the effects of vacuum on voiding in solder joints. And anytime you can pull a vacuum during reflow, whether it's convection or vapor phase, vacuum will dramatically reduce voiding, regardless of these other factors. But these systems can be quite expensive, and they aren't really commonly available out in the, I mean, they are commonly available, but not many of our customers use these type of systems. So in this presentation, these are the voiding factors that we're studying. Solder powder size, we're again taking a look at type 3 versus type 4 and type 5 solder powders. In terms of solder pastes, we have two different water-soluble lead-frees, solder paste B and solder paste E. And then we have two different no-clean lead-frees, solder paste C and solder paste F, which is a new low-voiding no-clean lead-free. We gave letter codes to these solder pastes, and they seem like they're out of order. Well, these letter codes were used in prior papers, so I wanted to be consistent. For every fill the void paper, we use the same letter codes for the same type of paste, so it's consistent throughout all of our data. In terms of solder alloy, we've never studied different alloys besides SAC 305. SAC 305 was the main alloy we've used in the past. So SAC 305 was included again as a baseline in this paper, but we've also added 3 different alloys in addition to SAC 305. You've got SN100C alloy, which is a tin, copper, nickel, germanium alloy. SN100CV, which is a relative of C. It's tin, copper, nickel plus bismuth has been added. And then we have what we call an AT mixture, which is a mixture of 90% SAC 305 and 10% SN100C. The resulting solder joint would have this composition. This particular mixture was designed in order to widen out the temperature range of melting and freezing, so that the gases have more time to escape in order to minimize voiding. Surface finishes were still varied again. ENIG and OSP were the 2 surface finishes we used. And then we did another stencil design on these QFN thermal pads. We took a look at 50 to 80% area coverage on the stencil design. Here's our experimental methodology. This is the circuit board that we used. We call this a PR test board. It has 2 sizes of QFNs that we use for voiding measurements. L1 through L4 is the large QFN. It's a 10 millimeter body, 68 lead. The thermal pad's about 8.3 millimeters in size. Then we have a smaller QFN, a QFN7, which is at locations S1 through S4. That has 48 leads, and it's got a 4.9 millimeter thermal pad. Both of these QFNs have a matte tin finish as the surface finish. In most of our testing, we took 80 void measurements. So we ran 20 boards per variation times 4 measurements on 1 component size for each data set. So each data set has about 80 void measurements in it. Here are the 4 different solder pastes that we're using and some more detail on these. The 2 water solubles are B and E, and they're shown at the top. Solder paste B was chosen because it has relatively high voiding in this testing. Solder paste E has relatively low voiding as compared to B, just for a comparison. Both of those are classified as ORH1 solder pastes, so they're very high activity halide containing solder pastes. Solder paste C and F are our no cleans in this experiment. C is fairly low voiding, typically speaking, and F is considered ultra low voiding as compared to C. Both of these are classified as ROL0 solder pastes. The alloys that we used are shown here, and here's the melting ranges. Now I've ordered these in order of increasing melting range. So the melting range gets wider as you go down this table. SN100C is a eutectic alloy. It melts and freezes at 227 C, one melting point. SAC 305 is not eutectic. It melts in the range of 217 to 220, so it has a 3-degree melting range. SN100CV melts between 221 and 225, so it has a 4-degree melting range. And then this AT mixture of SAC and SN100C melts over a 10-degree span, 217 to 227. The stencil design for most of our testing is shown here. This stencil design on the large QFN has a window pane with 65% area coverage of solder paste, and the small QFN has a window pane with 50% area coverage. We didn't do that intentionally necessarily. We just chose those as pretty standard IPC recommended designs for this size of QFN. We did make one experiment where we used a different stencil design. And this stencil design, the intention was to study what the effect is of area of coverage on voiding. So we varied the area of coverage from 80% area of coverage here in the upper left to 70% area of coverage of solder paste, 60 and down to 50% area of coverage. And you can see the number of bricks in the window panes change a little bit from one design to the next. Here's a breakdown on the exact designs that we used. I won't go over all of this detail, but the number of windows is shown for each area of coverage, the window size, then the web spacing was held constant. That's the one thing we wanted to keep constant, 8 mil web spacing. And then the paste area of coverage is repeated here from 80 to 50% on each size of QFN. So when I get to the data chart that I show this data, I will call out that this custom stencil design was used for that data set. Otherwise, stencil design number 1 was used for all these experiments. Here are the two refill profiles that we used. These are both linear ramp to peak type profiles, as you can see from the shape. There's no soak essentially in these. The ramp rates were between 1.5 to 2 degrees C per second for both of these. The time above liquidus was 60 to 67 seconds roughly for both of these, and that was measured above 220 C for the SAC profile and above 227 C for the SMTAI sieve profile. Peak temps are a little different between these two profiles because they are normally different for these two alloys. SAC 305 peak temp is centered around 245 C, which is the optimal. And for SMTAI it's usually about 5 degrees higher than that, so it's centered around 250 C. The profile length was supposed to be about 4.5 minutes for each one of these, and both of these are close. And then the alloys that we use these profiles with are shown here. So the SAC 305 profile was used with SAC 305 and the AT mixture, because the AT mixture is mainly SAC 305 alloy. The SN100C profile was used for both of the SN100C alloys. Here's the equipment that we used for this experiment. The printer that we have is shown here. We ran pretty standard parameters on the printer. 30 millimeter per second print speed, 1 pound per inch blade pressure, and a 3 millimeter per second separation speed. The pick and place that we used to place the QFNs is shown here. We have a 10-zone reflow and air convection reflow oven that we used for all of the reflow. And then this X-ray system is what we use to measure voiding on the thermal pads. And the voltage and current settings are shown here. Here is our first set of voiding results. Alright, this is our first data set. I'm going to go over the types of data analysis that we do and explain how we're presenting the data. All of our data charts will look very similar to this. This is a voiding result by component size. So you've got void area on the y-axis, and then your data set that for comparison are across the x-axis. In this case, we're looking at the QFN 10 millimeter body and the QFN 7 millimeter body. And you can see that the QFN 7 millimeter body looks like it has higher voiding than the QFN 10. We run a statistical analysis on this called a Tukey-Kramer HSD test, which is an honest significant difference test. That tells us whether these data sets are statistically different or statistically similar to each other, and whether that's significant to a 95% confidence level. And then the other report that we use to determine that is this connecting letters report. So the Tukey-Kramer analysis puts out this connecting letters report. It assigns letter codes to each data set. If the letter codes are different, then the data sets are significantly different. If the letter codes are the same, then they are not significantly different. In this case, the QFN 7 millimeter size generated a higher voiding, significantly higher voiding than the QFN 10. The means are shown here, 32% void area versus 22% void area. This was done with no clean solder paste C in the SAC 305 profile. And I believe this difference is due to the fact that we used two different stencil designs on these two components. The QFN 10 had 65% printed solder paste coverage, and the QFN 7 had 50% printed solder paste coverage, and that area of coverage certainly has an effect on voiding levels. So I'm pointing that out just so you keep that in mind as we look at future data sets. In some cases we ran both components, in some cases we just ran one size or the other size, And so if you see the total void area numbers all of a sudden jump up, maybe we were talking about the QFN 10 and then we switch to the next slide as QFN 7s, that would explain why they suddenly jumped up and they look higher than the last slide. So here are voiding results by solder powder size. This is with the QFN 10, water soluble solder paste B, and this is SAC type 3 versus SAC type 4 powder versus SAC type 5 powder. And you can see it looks like voiding goes down as you switch from type 3 to type 4 and type 4 to type 5. The Stuckey-Kramer analysis spits out these circles for each data set, and if the circles are not overlapping, then the data sets are different. And you can see that these data sets are different, and then the connecting letters report validates that. You can see each data set has a different letter code, which means they are significantly different in terms of voiding. Type 3 generated higher voiding than type 4, and type 4 significantly higher voiding than type 5. The mean values are 53% void area to 46% void area to 29% void area. So for this particular solder paste, switching to a smaller particle size of solder powder has a dramatic effect on voiding. It reduces voiding. We repeated that test with no clean solder paste C, and this is the smaller QFN, the QFN 7. We wanted to see what effect solder powder size had on a no clean rather than a water soluble solder paste. Look at these data sets. Type 3, type 4, and type 5 all have the same levels of voiding. These circles overlap and are concentric to each other, and the letter codes are all the same, which means all of these data sets are identical. And intuitively we know that because you can look at the mean values, 32% for each one of these three data sets. So switching solder powder size does not have an effect on voiding for solder paste C. Here's a third test on solder powder size. This was run with no clean solder paste F, which is a new low voiding solder paste. Again, this is QFN 7. Looking at the data sets, it might seem that the voiding dropped with type 4 solder powder, but type 5 and type 3 are giving very similar levels of voiding. The letter codes are all the same and the means are not different enough to make this significant. So what we can say is solder paste F is very similar to solder paste C in terms of how voiding is affected when you switch solder powder particle sizes. It doesn't have an effect on solder paste F and C, but it did have a big effect on the water soluble solder paste B. These are the voiding results for solder alloy. These were all run by water soluble solder paste B with the appropriate profile for the alloy, and these are run with QFN 7. This is the AT mixture, has relatively low voiding it looks like compared to the other data sets. This is SAC type 3, standard SAC alloy, again very low voiding compared to the others. SN100C type 3 was run in addition to type 4, and then also SN100CV type 4. We only had SN100CV available in type 4, so that's why we included type 4 SN100C for comparison directly with the same particle size. You can see some of these circles do not touch each other and some do, and if you look at the letter codes it really kind of explains what's going on here. SN100C type 3 and type 4 are the highest overall voiding with a letter code of A. The AT mixture and SAC are lower than that significantly with letter codes of B and C. S100CV is in the middle. It has letter codes of both A and B, which means it's similar to the A's and similar to anything with a B. So SAC alloy is overall the lowest voiding, whereas S100C overall highest voiding in this experiment. And this seems to be corresponding to melting point or melting range. SN100C has a singular melting point at 227 C, whereas the melting range for SAC is about 3 degrees, the melting range for the AT mixture is about 10 degrees, and CV has about a 5-degree melting range. So the wider melting ranges seem to have lower voiding than the single eutectic alloy. Here are the voiding results for surface finish. This is ENIG versus OSP. These were run with water-soluble solder paste B and the SAC 305 profile and on the QFN 10mm size. You can see these two data sets look almost identical. The circles are concentric and the letter codes are the same. And these mean levels are identical, 40% mean void area for both ENIG and OSP with this particular solder paste. This particular solder paste is highly active and it seems to wet and spread equally as well on both of these surface finishes. Here's the same data repeated for water-soluble solder paste E. This is also a high-activity water-soluble solder paste, and you can see the voiding levels look very similar here for ENIG and OSP. The mean values are 39 and 37%, and the letter codes are the same. So there is no difference in voiding behavior for this solder paste on these two surface finishes. Here's the same test repeated for no clean solder paste C. Again, we're looking at the difference between ENIG and OSP surface finish. You can see ENIG voiding is much lower than OSP voiding. The means are 9.2% versus 1.4% for ENIG. So for no clean solder paste C, it doesn't wet and spread as well on OSP surface finish as it does on ENIG. So that creates higher voiding from this particular solder paste when you change surface finish. But the same was not true for the water-soluble solder pastes. The water-soluble lead-frees had identical voiding for both of these surface finishes. Here are the voiding results for two of the solder pastes that we tested. I just chose these two for a quick comparison. These are no clean solder paste C and F, run with a SAC 305 profile and QFNs 7. Solder paste C has significantly higher voiding than solder paste F. You can see the mean values are 32 versus 25%. The letter codes are different, so this is statistically significant. So we can show that solder paste F, which is a low voiding solder paste, does generate lower voiding than solder paste C. These are the voiding results for the custom stencil design. So in this case, we varied the area of coverage from 80 down to 50% area of coverage, and we used no clean solder paste F and the QFN 7. You can see two different levels of voiding here. 50 and 60% area of coverage had significantly higher voiding than 70 and 80% area of coverage. You can see the mean values down here are quite different. 28 to 30% void area for the lower area of coverages to 6 and 7% void area for the higher area of coverages. So you can see here that just by increasing the amount of solder paste you print onto the thermal pad, you can significantly affect voiding. And that's largely due to the amount of wetting or spread that the paste can do underneath that component body. If you have too little solder paste, voiding goes up. And some of those voids are just due to incomplete flow of solder paste underneath the component. And then if you put on more solder paste, voiding goes down. But I will say this, that in the 80% area of coverage, we did have some component float and skew, which caused lack of connection on some of the perimeter pads. So 80% solder paste area is probably too high for these components. 70%, maybe 65% would be an optimal number of solder paste coverage to get the proper orientation of the component and also to minimize voiding. So here's our conclusion, or a summary of the data. So in conclusion, what have we learned about voiding? The component size has an effect on voiding. The smaller QFN gave higher voiding than the larger QFN that we tested, but this was likely impacted by the stencil design that we chose for the standard stencil. The standard stencil had 50% area of coverage for the small QFN and 65% area coverage for the large QFN. And that probably had a bigger impact on voiding than the two different sizes of components. This is something that I'm looking at studying a little more in the future. I'm going to design some stencils where we have the exact same area of coverage and run both component types, and we will see what types of voiding levels we get. Solder powder size had an impact on voiding as well. Decreasing the solder powder size gave lower voiding for water-soluble paste B, but it did not have any effect for the no clean solder paste C and F. Solder paste by itself has a big impact on voiding. Water-soluble lead-free pastes tend to give much higher voiding levels than no clean lead-frees. And there are also new low voiding solder pastes available that can help to reduce the potential for voiding. Solder alloy had an impact on voiding. The melting range of the solder alloy seems to have an effect. As it widens, voiding levels seem to go down, but that's not just the only factor with solder alloy. the surface tension of the solder alloy might play a role, how well that it wets and spreads on the metal surfaces of the component in the board might play a role. So there are other factors to think about when you're looking at different solder alloys. Surface finish had an effect. With no clean solder paste, OSP gave much higher voiding than ENIG. But two different water-soluble solder paste showed very similar voiding levels with OSP or ENIG. And then the stencil design had a big impact on voiding. Increasing the printed paste area tended to reduce the potential for voiding on these QFN thermal pads. So here are some recommendations on how to fill the void. Decreasing the solder powder size can reduce voiding with certain solder pastes. So if you have the ability to change your solder powder particle size, it might have an impact on voiding. If you also have the ability to change solder alloy, changing solder alloy might help to mitigate voiding. But that's not true for every solder paste. The alloy and the solder powder particle size have to work with the paste that you're using. We recommend using a solder paste that works well and wets well on all the surface finishes that you're using, or change the surface finish. If you can use a surface finish that's easier to wet, then that's going to minimize the potential for voiding. Lower voiding solder pastes are available and can be used to reduce the overall potential for voiding, but I will say that with a caveat that solder paste is not the only factor here. There are lots of other things that affect voiding, as we've shown in this data. And then we recommend that you optimize the stencil design to allow for complete wetting and add gas escape routes to allow voids to escape from underneath, especially these low standoff leadless components. Here's a list of the future work that we're planning on testing. We are going to take a look at voiding for via hole and pad designs. Via hole and pad are quite common circuit board designs for QFNs especially, and we are testing a couple different ways of mitigating voiding for this type of design. We're looking at via hole plugging options. So as a baseline, we're going to run some via and pad designs without any plugging, just to see what type of voiding level we get. And then we're going to try to do a solder mask tent on the back side of the circuit board, or the non-soldering side. See what effect that has. Solder mask tenting tends to put a thin layer over one side of the hole, but the rest of the hole is open. So there's going to be air or maybe process residues in that via hole that could potentially escape up into the solder joint and create a void. Solder paste can still potentially flow down in until it hits the solder mask tent on the bottom side. So we'll see what effect that has. And then we'll do a complete via fill process as well, which is known, and the popular theory is that the complete via fill will reduce voiding completely. But we're going to test it. We're going to see what effect that has. And then in terms of stencil design, we're going to try our solder paste print around the holes, and we're going to add some gas escape routes to try to optimize that stencil design so that solder paste can't flow down into the via very easily, and that any gases that might come out of the via can escape from underneath that component body. And then we'll compare that stencil design to a standard stencil design where we print window panes directly over the via holes, ignoring the via holes completely as if they weren't there, and we'll see what effect that has on voiding. So in terms of acknowledgements, I had some help working on this paper. I'd like to thank Greg Smith with Blue Ring Stencil for his help designing the stencils used in this paper. And then I also appreciate the efforts of Andrea Motley, a summer intern who performed much of the testing and gathered much of the data that I showed here. Thank you. And if you have any questions, please email or call us at that phone number, and we would be happy to help. Have a great day.